the kinetics of electrode reactions. The reaction rate is a strong function of a potential, and thus we require potential dependent rate constant for an accurate description of interfacial charge transfer dynamics we have discussed earlier. So here we have analyte species A, which is reduced to species B with the forward rate constant Kf, and that is also oxidized to species A with the backward rate constant Kb. This system is at equilibrium or reversible because, in the case of OCP, where the system is in equilibrium and the condition is open circuit, and here the species is at particular voltage is either oxidized or reduced. So the forward rate constant rate of rate of reaction expressed in term of forward rate constant is written here, and we have a rate of backward reaction with backward rate constant, and the overall net change in the rate of reaction is the rate of forward reaction minus rate of reverse reaction, and at equilibrium we know that the rate of forward reaction over the rate of backward reaction is equal to the K equilibrium. So this K equilibrium constant is equal to concentration of reduced over concentration of oxidized species. Here the kinetics describe the evolution of mass flow throughout the system, including both the approach to equilibrium and dynamics of maintenance of the state. The thermodynamics describe only equilibrium, whereas kinetics describe the balance quantity, which means that thermodynamics describe how this equilibrium condition is achieved, whereas kinetics explain the rate of the electron transfer, that is forward or backward in this case, at the equilibrium condition. The equilibrium constant is expressed in terms of Arrhenius equation, where EA is the change in internal energy that is going from one of the minima to a maxima, which is called the transition state or activated complex. The energy of activated complex or transition state is expressed in this form, and the enthalpy of activation would be equal to change in internal energy plus work done by the system. As we can see that the system is in equilibrium, this work done is equal to 0, so enthalpy of the system is equal to the internal energy of the system. Hence we can write the Arrhenius expression in terms of enthalpy, and enthalpy is expressed in terms of Gibbs free energy and entropy using this equation. So overall Arrhenius equation have been modified in terms of Gibbs free energy change of the system. That this Gibbs free energy change is for the transition state, and here K is the equilibrium